This is Dr. D. Govardhan, Professor in Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today, we are discussing introduction to simple stresses and strains in mechanics of solids. This introduction to stresses and strains. When a load is attached to a hanging wire, it elongates. Elongate means the length of the object is increases. But at the same time, the cross section of the wire is decreases. The amount to which the wire elongates generally depends upon the amount of load that is suspended, nature of the material of the wire, cross section area of the wire. But experimentally it is found that after some times, that is when the load is attached to it, it elongates, but after some times it will come in equilibrium conditions. That is, it will not further elongate. It is only because of the cohesive forces between the molecules of the hanging wire that is exists, which is always oppose the deformations, or in other words, it offer resistance force to the deformations. And the resistance force which is equal to the applied load, the deformation starts. But if the resistance offered by the molecules, if it is less than the load that is applied, it elongates further and break the wire. The resistance offered by the materials of the body to oppose the deformations is called strength of materials. The strength of materials generally it is a stress and strain relations and found by particularly UTM machines, universal testing machines. Here the stresses here experienced so that the materials when it is subjected to load either may deform or the break depending upon the magnitude of the load, nature and cross sections. But here the force divided by the area of the cross section of the wire is it as a stress now. Mathematically, the stress is equal to the force per unit cross sections. In SI units, the stress is generally expressed in terms of Pascal, which is also equal to Newton per meter square. But for bigger stresses, megapascal and gigapascal is also used. The strain now. When a force is applied on objects, the deformation is taking place now. Here example, when a wire is there now, when the load is applied on it, the length of the wire is increases. Here assume delta L is representing the change in length of the body and L is representing original length of the object. The change in length is only due to the application of the external forces on it. So earlier we discussed stress is equal to the force applied to the, it is the ratio of the force applied to the cross section area of the wire. Here the strain is defined as the change in length of the object to its original length. Hence the units for the strain is it is only dimensionless because change in length by original length and it is not at all having any units now. Depending on type of the forces which are acting on the body, Different types of stresses as well as the strains are produced. No, these are classified based on the type of the load that is acting on it. These are classified as tensile stress, compressive stress, shear stress, and thermal stress. And types of strains are tensile strain, compressive strains, shear strain, volumetric strains, and temperature strain. Tensile stress and strain. When an object is subjected to the two equal and opposite pulls, because of which if the length of the object is increases, as shown in figure, the stress induced in the object is called tensile stress. Here example, it's a shaft is there, two equal and opposite forces are acting on it to pull the object. Here this is representing the original length of the object. Because of application of the load on it, that is the tensile force, the length of the object is increases further delta L now. The ratio of the applied load to the cross-section area of the object is called stress. But because of this stress, the length of the object is increases, the type of stress is called tensile stresses. The change in length to original length of the object is called strain. Since here the object length is increases, the corresponding strain is called tensile strain. Compressive stresses. When the section is subjected to two equal and opposite forces in such a way that the length of the object shorten its length, then the stress induced in it is called compressive strength. Here the object is there now, L now. Because of application of the force, this is called push force now. If the load is applied on it, the length of the object is decreases. Here the stress, it is called force per unit area of the cross section. But here, because of application of the load, if the length of the object is decreases, this type of stress is called compressive stress. The corresponding strain is called compressive strain. The words compressive, it means representing the length of the object is decreasing. Shear stress and shear strain. When a section is subjected to two equal opposite forces acting tangentially across the resisting section, the stress induced in it is called shear stress. Example, here this is representing here the object. Two equal forces, one is nothing but this directions, one more is in opposite directions acting on it. Now, because of application of forces, these forces are parallel to each other and acting tangentially to the surface of the object. The distortion is taking place as shown in figure now. That is, earlier that object is represented as a B, C, D. Because of application of the tangential forces, it is discharged as A, B, C1 and D1 now. So here the force for the unit cross section of the object is called here shear stress. Corresponding strain that is produced is called shear strain. Here in this case, if L is representing the length of the cube we are taking here now, it is discharged to D to D1 or C to C1 now. Now shear strain is represented as here now DD1 divided by AD, or it is also equal to CC1 divided by CP now. So which is equal to the, according to the trigonometric relations, it is equal to tan pi now. That is tan pi is equal to dd1 divided by AD now. Or which is equal to cc1 divided by here cb, which is equal to cb is equal to here length of the object now. The stress is equal to here now, already I told it is the force per unit area of the cross section. P is the force that is acting just over the surface tangentially. If it A is representing the this area of the cross section which it is acting now, the force divided by the area, here it is called the stress, because the stress is nothing but discharging the objects. Here, moreover, it is acting tangential to the surface. Hence, the stress is produced here. It is called shear stress. Volumetric strain. Whenever a body is subjected to a single force, or sometimes system of forces, it undergoes some changes in its dimensions. Example, here I am taking the figure number 1. When force is acting, that single force acting on the surface P now, the length of the object is increases. At the same time, the cross section area of the object is decreases. The cross section means it is the product of length and breadth and thickness. Both the dimensions are decreasing now. So because of all these things, the volume of the object is changing when it is subjected to the certain forces. It is also happened when the object is subjected to the several forces. Here we have taken the forces which are acting along the x directions, y direction as well as the z directions in figure number 2 now. So because of object when it is subjected to single force or the forces in 3 perpendicular directions, the volume of the object is changing now. So the ratio of changing volume to its original volume is called volumetric strain. Generally, delta V is representing the change in volume. If V is representing original volume of the object, the ratio of change in volume to the original volume, generally it is represented as here volumetric strain. Here mathematically, here it can be represented as delta V by V now. Here this volumetric strain can be determined for the objects when it is subjected to a single force acting along the axial directions, or when the body is subjected to 3 mutual perpendicular forces. Thermal stresses and strain. Whenever the temperature of the body increases or decreases, the length of the object is also changes. That is, when the temperature increases, generally the length of the object is increases, and when temperature decreases, it is the contract or the length of the object decreases. Here I am taking the object now. Just assume it is having 100 mm length at 0 degree centigrade now. When the temperature of the object is raises to 50 degree centigrade, generally the length of the object is increases now. When it is allowed to increase its length freely without having any supports, and without keeping any support like it to prevent its expansion, there is no stresses induced in it now. But assume just when it is increased to 50 now, the length of the object is increased further to 105 mm now. That is the 5 mm length of the object that is increased only because of change in temperature from 0 to 50 degrees. Now when the supports are kept to prevent deformations, when the temperature of the object is increased from 0 to 50 degrees, then stresses are induced in it. These are nothing but, the support is nothing but having the reactions over the object to prevent its expansion freely now, when the temperature of the object is increasing now. Hence, the compressive stresses are developed in it. Here, there no external forces are acting on it, but these stresses are only induced in the object when it is preventing its expansion freely when the temperature of the body is increasing. These type of stresses induced due to change in temperature are called thermal stresses. The corresponding strains are known as thermal strains, or it is also called temperature strains. Here I am taking an object now, that AB, of length L at 0 degree centigrade now. Here two supports at A and B are kept to prevent its expansion freely when the temperature of the object increases. It will also prevent the contraction of the object when the temperature of the body decreases. Here L is representing the original length of the body. Assume the temperature of the object increases to T value from 0, and alpha is representing the coefficient of linear expansion of the materials. So because of increasing temperature, the increasing length of the object is given by the mathematical relations delta L is equal to L into alpha into T now. When it is allowed freely now. But according to when the thermal stresses are induced in the body, when the supports are kept to prevent its expansion when the temperature of the body increases now. Hence, when it is fixed between the rigid supports, the expansion is prevented, hence the compressive stresses are induced in the bar now. Here, according to the equations, delta L is representing the length of the object increases when the temperature of the body increases to T, that is delta L is equal to L into alpha T. Here L into alpha T now. Here delta L by L, it is equal to alpha into T now. Where delta L by L is equal to the change in length to its original length. This is called strain now. This strain is only produced because of increasing in temperature. This strain is called temperature strain, or it is also called thermal strain now. Now, the ratio of stress to strain is always the constant according to the Hooke's law. And so, here I am taking this nothing but equal to epsilon now. That is sigma divided by this epsilon is nothing but it is called a constant. Here yes, sigma is equal to, we can take it as E into epsilon. Epsilon is equal to already alpha into T, that is called strain into E now. This is called stress now. But these stresses are produced without external forces acting on it. It is only because of change in temperature of the body. Hence, these stresses are called thermal stresses. These thermal stresses, when the expansion is prevented, the thermal stresses which are produced in it are called compressive in nature. When the temperature decreases, it is not, the supports are not at all allowing contractions, hence tensile stresses are produced in it. Here the stresses and strains of a materials generally measured by using universal testing machines as shown in figure. Here this is the specimen made as per the Indian standards. These are fixed between the fixed jar as well as the movable jar of a universal testing machines. When the load is applied on it gradually, that length of the specimen is increases at certain point it breaks into parts now. So by drawing the stress and strain relations at various loads, the curve which is obtained is known as stress strain curve. This is most important for understanding the mechanical properties of the materials, which are most useful in designing when the object is subjected to certain loads. Here we are discussing true stress and strain now. Yes. Because earlier we have taken the stress is equal to force by area. The area of the cross section is representing the initial area of the cross section. But just now when we discuss here now, in the specimen, when the load is applied, the cross section of the specimen is gradually decreasing now at every instant. Finally, it is now separating into parts now. So the ratio of force by area is called strain now, stress. But here every instant the cross section of the area is changing now. Hence, the ratio of force applied to the area of the cross section at that instant is called true stress, and corresponding strain is called true strain. That is, the true stresses and strains on the other hand based on the actual as well as the instantaneous dimensions and are better representation of deformation behavior of the materials. The stresses, true stress strain curves continues to go up till the fractures takes place. It's based on the actual engineering stress and strain curve or true stress strain curve. Stress and strain curve. For studying the mechanical properties of the solids, the information regarding their elastic properties are most important. This can be obtained studying the stress strain relationships under different loads using stress strain curve. It can be drawn by keeping specimen continuously under gradually increasing load by universal testing machines. The engineering stress and strain curve is based on original area. It descends after maximum load as the loading bearing capacity of sample decreases due to the reduction in area. The stress strain graph has different points as well as the regions. Each part is having important significant for the designing of a product. These are proportional limit, elastic limit, yield point, ultimate stress point, fracture or breaking point. Here this graph is representing stress strain curves for the mild steel. It is drawn stress versus strain as shown in figure. Stress is in horizontal directions, strain is in horizontal direction, stress in vertical directions. When there is no load acting on it, that is the stress produced as well as the strain produced equal to 0. Hence, it is represented as an origin. When the load applied on the specimen, when it increases, the elongation also increases. That is, when the force increases, the elongation also increases. But here the force is always taken in terms of force by area. that is in terms of stress. The elongation produced, it can be taken in terms of strain, that is change in length to its original length now. That is elongates means the change in length is also increasing now. Now up to A point, it is almost in the form of line only. It is called here now proportional limit now. Or in other words, up to A we can say when the stress is increasing, the strain is also increasing continuously. The ratio of stress to strain is almost the constant. That constant here called here elasticity now. It is a property of the materials. Now after A to B now again, even though just on increasing the load which is acting on the specimen, the strain produced also increasing, but it is not at all proportionate. Hence, the shape of the curve is in the form of curve between A to B now. Okay, this B point is called here now elastic limit. That means after removal of the forces, even though it is elongated up to B, the bar or the specimen will come to its original shape after removal of the forces. Hence, it is called elastic limit. It is also called yield point. From B to C, if you observe, even though without increasing in load on the objects, it is elongates just B to C. That is without applications or decreasing the load also, it elongates from B to C. And after C point, it is continuously, when the load is increasing, the elongation is also increasing, but not according to the proportionality now. So the point C is called lower yield point, at which from B to C, the plasticity region starts now. That means even though if you remove the load, it will not regain its original shape later now. So after behind C point, C is called lower yield point now. From C to D, on increasing the stress, that is the load, the elongation also increases. At D, it is called just a breaking stress, no ultimate stress. It is there. Afterwards, without applying the loads, the elongation continuously increases till fracture taking place now. If we observe these regions now, here now, the regions between O, A dash now, this is nothing but area under which the Hooke's law holds good. That is, the stress is proportional to the strain now. Now, the area under O, B and B dash, this is called elastic region. That is, on removal of forces, the object regained its original shape. But after this B dash to E dash, this area, which is represented here now in yellow color now, this region is called plastic region. Here in which even though the forces are removed, it will not regain its shape later now. So these are the various regions that are divided under stress strain curve to study the properties of the mild steel. Okay, I am giving this once again the points. The first one is proportional limit. It is the regions in the stress strain curve that obeys the Hooke's law. In this limit, the ratio of stress to the strains, which gives the constant values, it is known as Young's modulus, and the point A is called here a proportional limit now. Elastic limit, whenever some external forces which are acting on the body undergoes deformations. After removal of the forces, if it is come back to its original state, then it is called elastic properties. But here the point E is representing, here B point is representing the graph, it is called yield point. Just behind this point, even though remove the forces, it will not regain its original shape, but before that point, the object will regain its original shape and remove the forces. The yield point B is defined as the point at which the material starts to deform plastically. After yield point, it passes the permanent or the plastic deformation taking place now. These yield points are classified into two types now. One is the upper yield point, one more is the lower yield point. Ultimate stress, it is a point that represents the maximum stress on the curve or the materials induced before failures. Beyond this point, the failure that is elongation starts even though the load is not applied, that with the load state continuously, that elongates further, it further it fails. The F is representing the fractures at which the specimen breaks, and the load at which it breaks is called here failure. That is represented here now. The point at which it fails is represented as a F now. Hooke's law. Here the scientist, English scientist Robert Hooke, he noticed that when the material is loaded externally, the deformation is taking place now. Here, when the just single force is acting on it now, like this, when you are taking specimen, this force is called a tensile force. Because of application of this force, both are equal magnitude acting in opposite directions. The length of the object is increasing now. For all the objects here, the stress strain relation. Stress means the force, it is the ratio of force to the area of the cross section, and the strain is the change in length to its original length because of application of the load. When he observed, the stress strain relationship is almost the same for the most of the materials. Hence, here the ratio of the stress to strain is always the constant. He observed now that constant is values may be differ from one material to another materials, but he called that constant is known as elastic constant. The elastic constant is here it is its values differ for the different materials, but stress to strain remains constant within the elastic limit. Here margins of elasticity are Young's modulus. It is defined as the ratio of stress to strain. This value is different for the different materials. For the steel, it lies between 220, wrought iron 190 to 200, cast iron 100 to 160, copper 90 to 110. These properties, that is the Young's modulus properties, which is obtained by using the stress and strain relations, is the most important in designing the materials. And by using the stress and strain curve, the designer can decide how much load that can be applied over that materials without failures, and also what is the safety factor that he has to keep in order to prevent its failures later on. Okay, this is the important topic for the design engineering, to identify the various points on this stress and strain curve. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.